This is a quick tutorial on acid bases for my students in level 1, level 2, and level 3. Acids and bases are used everywhere in life, so we will learn a little bit more about them and some of their features. Now, I'm not going to spend a lot of time on this slide. You can pause the video and learn this, but for our intensive purposes for what we need to do for this chapter, these are the properties of acids and bases that I'm most interested in you learning. And quickly, there are a couple of differences between the two. First of all, in the acid world, the acid is always going to start with an H for our intensive purposes, for example, HCl. And our base is always going to end in OH. Okay? Base is going to end OH, and so NaOH aqueous. Remember, the aqueous means that it's dissociated in water, so H plus ions and Cl minus ions, and Na ions and OH minus ions. A couple of differences between the two. Your acids will taste sour. Think about Sour Patch Kids. Your bases will taste bitter, something like a bitter lettuce. The acids will turn blue litmus paper red. So it's going from blue, basic, to red, acidic. And the other one will turn red, litmus paper. The base will turn red, litmus paper, blue. So you can just basically say base is blue, all right, acid is red. An acid will give you a clear phenolphthalein solution. Phenolphthalein is an indicator, and a base will turn phenolphthalein pink. There's a couple of things that it'll react with to form H2 and CO2 gas. The other critical thing is that the pH of an acidic solution will be less than 7. What I mean by that is it'll be like pH of 1, pH of 2, pH of 3, etc., etc. A base is going to have a pH of 7 or greater. Greater than 7. 7 is neutral. The only thing that's really similar about the two is that they both will conduct electricity. They're electrolytes, and remember we learned about electrolytes before. So there are two types of acid-base systems that I'm most interested in you learning. First one is Arrhenius acid. And an Arrhenius acid is a substance that is going to ionize in aqueous solutions, in other words water, to produce H plus ions. So here we have our acid here, HCl. It's going to ionize into H plus and Cl minus. And you also may see this at some point in time written the following. You might also see it written as H3O plus, which means that the plus ion, the proton, has associated itself with the water molecule. All right, and then the other thing that we have to be cognizant of is that the Arrhenius base is going to be anything that ends in OH and forms OH minus ions in aqueous solution. So here's my NaOH aqueous. It forms Na plus ions and OH minus ions in solution. So the takeaway is Arrhenius acid forms H plus ions. The Arrhenius base forms OH minus ions in aqueous solutions or water. The other type of system that I want you to be very familiar with or learn is the Bronsted-Lowry acids and bases. And the definition of a Bronsted-Lowry acid is a proton donor. So it's going to donate a H plus species. And the Bronsted-Lowry base is a proton acceptor. Donates, accepts. The only thing that's getting transferred is this H plus thing. So one is donating it to the other. So the acid is donating it to the base. And we'll talk about that in a little bit more when we show some of these examples. So things to take away from this slide is you have to know the definition of Bronsted-Lowry acid and the definition of Bronsted-Lowry base. So let's see how this Bronsted-Lowry acid work. So we have this acid-base reaction here, and we need to understand which one of these two there are, out of the 4 species, 2 of them are the Bronsted-Lowry acids and 2 of them the Bronsted-Lowry bases. So let's look at the forward reaction first. So the forward reaction, remember, goes in this direction here, this direction. So from here to here. And so we said that the Bronsted-Lowry acid is going to be one that donates a proton. So what I look like on this side of my equation is I look over here and see what species I have, and then I look over here to see where the proton has gone from and where the proton has gone to. So we have protons over here, the H2s. So one of these has to go someplace. So let's just draw where that's going. We have one of these protons here is going to donate to this species here to form this species here. So the thing that's donating the proton is our acid. So one of our things is our acid is going to be H2O. Okay, so let's put that here. So we know that C and D are wrong because none of those have the H2O as an answer. Now let's look on the other side of the equation, right? So remember, these are forward and back, so there's also equilibrium going this way. Now I look on this side here, and I said, okay, so I have 2 protons here. Which one is getting donated to form this side here? It has to look like this when we're done. So the only way that happens is when we take this proton here and donate it back to this OH minus. So when you're done with that, you'll see that you get H2O here and CO3 minus here. So in this case, the HC3O minus, HCO3 minus is my acid and my base is my OH. So the answer for this particular problem is going to be H2O and H3O plus. All right. So remember, we're looking for the things that are donating the protons. So in this case, remember, one of these hydrogen donates it to here to make it look like this. And in this case, this species here donates a proton to make it look like this and this. So on the same note, let's see if we can solve this one together now. Now, which one of these is going to be the proton donor on each side of the equation? So remember, the double arrow here, the double arrow means it's an equilibrium, so it's going forward and back at the same time. So which species acts as the Bronsted-Lowry base now? Right? So not the acid, the base. So which one of these species is going to be accepting the proton? Accepting the proton. So let's see what our things are. So if we look on this side of the equation here, we need to make this side of the equation, when we donate the proton, to look like this side of the equation. So one of these species has to accept the proton, and one of these species has to accept the proton, and one of these species has to donate the proton. Now I have an HS minus here, but I have an H here. So what's going to happen is this proton, one of these protons here, is going to donate it to this to make it look like this, right? So if this is if this one is donating, then the S2 is the one accepting. So that would be my base on this side of the equation here. On this side of the equation here, if we did it the reverse, right? Now, I want this side, when I donate my proton, to start looking like this side. So how am I going to do that? Well, the only way to do that is to donate the proton that I just donated from this side back to the OH. And so my OH is my Bronsted-Lowry Bronsted-Lowry base on the reverse reaction. So the answer to this question is, which species acts as the Bronsted base in the forward reaction? Remember, forward's going this way, so my S2 is going to be my answer. As a result of Bronsted-Lowry acid-base theory, we are now able to understand that 2 substances that are related by the loss of gain over a single hydrogen ion are called acid-base pairs. So let's see how these work. So when we remember before, we said that the Bronsted-Lowry acid was the thing that was donating the proton, and the base was the one accepting the proton. So you're going to have a conjugate acid and a conjugate base. You have an acid and a conjugate acid, base and a conjugate base. So let's see what those are. The conjugate acid is the particle formed when a base gains a hydrogen ion, or the proton. All right, we can just all write here, or the proton, the H plus. It's proton, which is the H plus. Okay, so that is the hydrogen ion. And then the conjugate base is the particle that remains after the acid has donated a hydrogen ion. Right? So let's see what that means in real life. So let's quickly just erase this. All right, to give me some room. So let's look at HCl on the bottom here. HCl, we know that that's always an acid, right? So that's going to donate a proton, which is this species right here. That's going to donate it. What's left over after it has donated that proton is the base, which is the Cl and Cl minus, right? Cl minus, because don't forget, this is really H plus and Cl minus. This is really H plus and Cl minus, right? Because they're dispersed into water, it's aqueous, and they disperse into ions. So after I get rid of my proton, I'm left over with what the base is, the conjugate base. So after I get rid of my proton, again, after I get rid of my proton, I'm left with the Cl minus here, right? And that is my conjugate base, right? It's not the base per se, but it's the conjugate base because that's what I'm left over with, right? So now that's able to accept a proton later on. And what is my conjugate acid? Well, the acid is the particle that forms when a base gains a hydrogen ion. So here's my initial base, and now when I gain a proton, that's my conjugate acid. All right, so it's opposite. So now that we understand what the difference between a conjugate acid and a conjugate base are, and a regular Bronsted-Lowry acid and Bronsted-Lowry base, we now know that they are related to each other because it's just the position of where the proton has transferred from and to. So let's see how this works. Remember, the conjugate pair are related because the only difference between the two species in the pair is the location of the proton. All right, so in the first case, let's look at HCl. Once HCl here donates its proton, it forms the conjugate base. So let's just label that here. So here's my acid, and on this side, which is my conjugate base. All right, and now once the base here, so remember we're donating this particular proton here is getting donated to here to form the acid on the other side. Now this is the base, and now this becomes the conjugate acid. Because on the other side, remember, the other side is now this has this proton. It's going to donate it back to the Cl to create this here, right? The species. These two are related because once I donate the proton, it looks exactly like this side. So the difference between this species here and this species here is one proton. And the difference between this species here and this species here is one proton. So they are the pair, right? The only thing that's different between these two is the proton, where the proton is located. And the only difference between these two is a proton. So that's why they are called pairs. All right. So let's look at it down here. Here's another example of this. We're just going to talk about adding ammonia, which is NH3, to water. Now in this case, the water is the acid because it's donating a proton to the base, which is these lone pair electrons here. Now once the water has donated its proton to the base, the ammonia, now it becomes the conjugate base on the other side. So let's see how that works, right? It's donated its proton, and now what's left over is this part of the thing, which is the conjugate base over here. Once this accepts the proton, the base accepts the proton, it looks like this side here, and this is the conjugate acid. So basically what you're seeing is that once the proton is transferred, the base subunit becomes the acid, and the acid, refraction of the acid remaining, becomes the base on the other side. The conjugate acid is from the base unit, and the conjugate base is from the acid unit. So it's almost like they're opposite. Okay, I'm not going to spend a lot of time on this because you should have a lot of practice on this in the next couple of slides. But let's just quickly talk about the pH scale. Now, the pH scale is the measurement of the amount of H plus or H3O plus in solution. So you're going to see these things interchanged equally, right? If you see H plus, you can assume it's the same thing as H3O plus for the calculation, and H3O plus is the same as H plus for this calculation. Okay, so when you add an acid to water, it produces this species called H3O plus. The H plus ion attacks one of the, not attacks, but it bonds to one of the oxygen atoms in the H2O molecule, and therefore it just becomes this species here. Now, the way we define the pH is the following. It's the negative logarithmic scale of the concentration of H3O plus. It ranges from 0 to 14. And now here's the kicker. The concentration of the H3O plus gets bigger as you go from 14 to 0. So in other words, 14 is lower in concentration of H3O plus than 0 is. It's reversed because it's the negative log scale. Now here's another quick thing that you should be very familiar with. A change in one pH unit on the scale, a pH of 0 to 14. So in other words, if you're going from pH of 1 to pH of 2, that change is tenfold in the concentration of the H3O plus species because it's the log. So a pH of 2 is 100-fold, right? Therefore, small changes in the pH are large numbers for concentration. And remember what I said before, anything that's less than 7 is going to be acidic. Anything that's greater than 7 is going to be basic, or in other words, alkaline. The only time that something is neutral is when the pH is exactly 7. And remember, when we talk about the log of the concentration, we're talking about the molarity of that, right? So you should be pretty familiar with how this thing works. Now, I will give you these equations on the quiz or test, but you need to understand the relationship between pH, pOH, H3O plus concentration, and OH minus concentration. So this little diagram should help you out. Now, there's a couple of key equations here. There are 6 equations that you should be very familiar with and know how to use. Let's look at the first one. So the first one is my pH, right? My pH is going to be defined as the negative log of the H3O plus concentration, or the H plus concentration. All right, so that'll give me pH. That's this way, right? So if I give you the concentration of the H3O plus in solution, or the concentration of the acid, then you should be able to say, okay, now I know what the concentration of the H plus is. I should be able to calculate the pH, right? However, if I give you the pH, you should be able to calculate the H3O plus concentration. That would be done by this formula here. It's just the 10 raised to the negative pH. So let's say the pH was, let's say the pH was 2. Let's say the pH equals 2. It would be 10 raised to the minus 2 to give me the concentration of this. All right. So let's see how we can now, let's see some more of these here real quick. The other way is this thing called pOH. Now, pH is what we normally going to talk about, but the other opposite thing that you can talk about is pOH. And the pOH is just the negative log of the OH minus concentration. Same thing as the other one. pOH is the, and then if you wanted to get the concentration of the OH, it's 10 raised to the minus pOH. And you can see here scientific numbers and notation should be placed in parentheses. So when you make your calculation for your calculator, you have to go something like this with your calculator, and you should practice that. Now, there is a relationship between pOH and pH, and this is a relationship that you should really be familiar with. The pH plus the pOH will always equal 14. So if you know one, you should be able to back calculate the others. For example, if I give you a pH of 3, you should tell me that the pOH is 11. Right? And on the other side, if I give you the concentration of this times the concentration of the OH is always going to give me 1 times 10 to the minus 14th. Notice how they're related here. It's just the log of this times the negative log of this, right? Here's the negative log of this, which is 14, and the negative log of these other ones would give you the other pH and pOH. All right, now the last thing to know is that when you translate on all these, okay, when you translate to all these, you have to be cognizant that you understand that there is a relationship between each one of these things. So pH and pOH are related by this equation right here. H3O plus and H3O plus concentration and OH minus concentration are related by this equation here. pH and the concentration of H3O plus are related by these equations here, right? And the OH, the things down here. So you should become very familiar with this 4 square box, right? If I give you the pOH, you should be able to get to any 4 corners of the box. If I give you pOH, you can go calculate the pOH and then calculate this from that. If I give you this, you should be able to calculate this you should be able to get the pH by either going either one of these roots, either this root here or this root here. All right? So that's the way you should work on this. So become familiar with all these. Again, I will give you the formulas, but you should understand the relationship between them all. So what I would like you to do here, and this is part of your homework assignment from before, but is you should get some practice in filling in these tables here. So I gave you one of the 4 corners in that diagram in the previous slide, and you should be now able to calculate all of these parameters. So let's just quickly do the first one together. So I have the concentration of this concentration here of OH3 minus, right? So for my pH, I'm going to write the equation over here. It's going to be the minus log of that number, and that number is 2.35 times 10 to the minus 3. Sorry for the thing here. So you're going to enter in your calculator. You would put log of this number minus log of this number on your calculator button, and you should get a pH of about 2.62 or 2.63. So let's just write that here, 2.63. Now, using my knowledge, and that's 4 square thing, if I have a pH of 2.63, then by definition 14 minus 2.63 is equal to 11.37, and that's my pOH. All right, that's my pOH, and then from this value here, I should be able to calculate my OH value, because it's just going to be 10 raised to the minus pOH, which is minus 3.37. And that answer is 4.26 times 10 to the minus 12. All right, so you should be able to calculate each one of these things pretty easily by using those 4 equations. So in this one I've given you, for example, on this one here, let's just do another one real quick. right? In this one here, I've given you the pH, so the pOH is just going to be 14 minus that number, which is going to be 5 point, what is that, 6.8. All right. Now, the other thing we have to do is, let me erase some of this real quick. So you've already seen this, so you should be able to erase this, and then erase this. Once you understand what the pH and the pOH, you should be able to tell me if it's acidic or neutral. So in this case, we knew that the pH one here was, what was that? That was 2.63. So it's less than 7, so that's going to be acidic. And in this case here, the pH is greater than 7, so this is going to be basic. All right. So you should go in, I would stop the video here, fill in as much of this until you start to get comfortable with doing this. And then the next slide is all the answers for this table. Alright, so here are all the answers from the four for the slide. So you should do a self-check here. You know, there's a lot of stuff here to do. If you're starting to feel comfortable with it and gotten all the answers correct in the first 4 or 5, 6, 7, whatever slots, then I wouldn't spend any more time doing this. It seems that you understand the concept. If you struggled with this a little bit, you should read up and do some more practice. So titration, you should understand what the definition of a titration is, but the titration is to you use a titration to calculate the concentration and quantity of a unknown species using the concentration and quantity of a known species. And the way it works is typically you'll add an acid of an unknown concentration on the bottom here. So let's just show you where that is. That's here. Here's my acid with an unknown concentration. We do know the volume in here because we have to carefully put in the volume, so it could be something like 25 mils. We put our indicator in here. Remember what an indicator is. It's a species that will turn color once it reaches a certain pH. And usually the pH is somewhere around the neutral point, pH of 7. Some of the indicators are a little bit basic, so they'll turn around 8. Some are a little bit more acidic, and they'll turn around, around 5 to 6. But basically, it's somewhere around pH of 7. With the indicators will turn color. The phenolphthalein goes from clear in an acid solution to slightly pink or pink in a basic solution. Then in the burette, which is basically you could think of it as a very thin, highly calibrated, graduated cylinder with a stopcock. We put the base of the known concentration, and then we titrate in here until the color changes, and then we read off what the volume is that we added. So from the volume we added times the concentration that we know versus the volume of the system in here, we should be able to calculate the concentration of the acid in the flask here. And I'll show you how to do that in a minute. So the things we need here to make sure is we have the indicator, the base of the concentration, stopcock. This is a titration. So when we do a neutralization or a titration reaction, we're basically undergoing a double replacement reaction to produce salt and water. So here's the general equation for this. We have an acid, let's say HCl, and then we have a base, sodium hydroxide, and we mix them together, and they get neutralized. So they form a salt and water. So all acid-base things are going to form a salt and water when we mix them together. And let's see how that works here. So we have HCl. That's our typical standard, acid that we've been working with a lot. Sodium hydroxide, which is our base. When we mix the two, how it works is these are all in ion form. So we could actually write the equation this way. We have H plus and Cl minus, and then plus Na plus, and then OH minus. And remember what happens is we're going to donate the protons, so this is going to get donated to here to neutralize that, and then what we're left with is these two species here. And so when you're done, you get H2O and NaCl. It's a C, aqueous. And so that's what you get. So it's a salt. There's my salt, and here's my water. Now we can do neutralization calculations just as we've done for other types of similar systems. When we did dilution things, where we took the molarity and then times the number of liters. We also did this similar thing like this with Boyle's law, P1V1 equals P2V2, right? And it's the same setup as here. We have two variables. We have four variables, and the equation is the molarity of the acid times the volume of acid will always equal the molarity of the base times the volume of the base. Because what you're doing here is when you talk about molarity, remember what we did. Molarity is moles per liter, right? And then when we do the moles per liter, if you take molarity times liters, you equal moles. So again, we're equalizing the moles with each side of this equation. So the moles here equals the moles here, and because of this relationship. So let's see how this works. So if we have an acid that has one molarity and a volume of a known volume, we can calculate the volume or the concentration of the base if we know one of those two parameters. All right. Now the only thing that gets into a little bit of a situation here is this idea of monoprotic versus diprotic versus polyprotic. Now a monoprotic acid is an acid that only has one proton or one hydrogen. So let's see, HCl is one, HBr is one, HNO3 is one. Okay, so they're all ones because they only have one of these, one proton, right? Now a polyprotic acid is something that has multiple protons, right? So let's see what those are. Multiple protons. So H2SO4, H2S, H3PO4. All right, that's a 4. That's sorry, that's a bad way to write the 4. H3PO4. They have more than one proton or hydrogen associated with them. So each one of these protons, hydrogens, can act as an acid, right? You can lose both of these, so you have to account for them in the calculation. So we'll show you how to do that for a minute. And now the other thing too is not only is it for acids, it's also for bases. So some bases have more than one hydroxide ion. So here are some simple titration problems, and you should work through these. We did a worksheet on this. You've done this with the lab. But I set up the problem here, so let's just quickly walk through two of these to show you what I mean here. So what is the molarity of an HCl solution if 30 mils was just neutralized by 48 mils of 0.1 molar NaOH? So this is let's just assign the variables here. This is M1, or the M acid, and this is the volume of the acid equals molarity of the base times the volume of the base, right? So once we do that calculation, we isolate for M, and we get 0.16 molar. All right. Now the key is on the next problem, that there is a little bit of a trick to it, right? Not a trick, but just something to be aware of. In this case, we said how many milliliters of 0.1 molar HCl are required to neutralize 25 milliliters of 0.2 molar BaOH2, which is barium hydroxide. Now notice here we have two OHs, and both of those need to be neutralized with the acid, not just one, so two. So we need to account for both of those. So how do we do that? Well, the way we do that is once we set up our molarity here and our volume here, we need to put the 2 over here because there's twice as many of them now. So it's effectively like we're neutralizing twice as much solution because we have 2 protons that have to be neutralized for every 0.2 molar barium hydroxide. And so when we do that, we have 0.1 molar times the volume of the HCl. Remember, HCl only has 1 proton, right? Not 2, so we have to worry that. All right. Now the same thing happens on the last equation here, on the last one, right? The last one is the same, but except now instead of using the base being polyprotic, this is single protic, right? It only has 1 OH. The acid has 2 protons that have to be neutralized. So in this case, the 2 goes on the side of the acid. And if this was a 3, here, you would have to put the 3 over here. If this was a 3 here, you'd have to put the 3 here. So whatever the number of OHs and H's, you have to account for when you do your molarity constant calculation. Now, I'm not going to ask you too many of these things on any type of quiz or test, but you do need to be aware that it's just not a straight one-to-one issue. All right, so that's the conclusion of this quick tutorial on acid-base chemistry. You should spend some time on your notes to familiar yourselves with the finer details. I went kind of quickly through this, so spend some time and make sure you understand all these basic concepts.